empieza el seminario, yo me levanto y como,
Ahí lo que ha dejado Luis, toma. Joder.
Estamos ya, ¿vale?
me he comido 2 de cada.
Venga, Luis, que ya te vamos a ir.
Enciende la luz de la pizarra. Creo que saqué el interruptor. Sí.
A ver si se hace.
Vale, más o menos. Bueno, bueno, bienvenidos a todos y a todas, gracias por venir. Bueno, en esta sesión del Coloquio Junior, nuestro speaker es Restrepo Montoya, que bueno, su charla está titulada como Higher Order Elliptic Boundary Regularity and Frequency Problems. Así que, cuando quieras.
Ismail. So I think I'm going to give the talk in English because Jorgen is in here. Sorry. No, don't worry. So, as I said before, as Ismail said, I'm going to talk about higher order regularity for pre-boundary problems, but don't be this specific. I will introduce what a pre-boundary problem is to motivate why is it important to consider higher order regularity. So, as a framework, I'm going to consider a very broad family of pre-boundary problems that encompasses the models that are more frequent in the literature. So, first of all, what is a pre-boundary problem? A pre-boundary problem is basically an elliptic PDE, differential equation of the sort of the form, let's say, Laplacian of u equals f of u, in the set where u is greater than 0, and some boundary condition, let's say, g of u, the normal derivative of u equal to 0, let's say, on the boundary of the set where u is greater than 0. So why is this called a pre-boundary problem? Basically, this is called a pre-boundary problem because not only u is to be found in the problem, but also the boundary. So a priori, we don't know what is the set where u is greater than 0. Okay, so usually these problems appear in variational settings, that is in minimization problems. The family of problems that I have in mind is the following. So, given a domain O in a ring, let me define the energy functional given by where this is the positive part of okay, so I consider this family of functionals taking gamma between 0 and 2, and I'm interested in the minimizers of this energy functional. This energy functional is important because it appears in first media settings, or appears, for instance, in finance. This appears in finance when you want to understand what is the binding that you have in a call, for instance, in American options. And when you try to find the minimizers of this functional, you can take derivatives. Basically, what you do is to consider, let's say, f of t equals this for any phi compactly supported in the set where u is greater than 0. So I'm cheating in here because I'm assuming that I already know that a minimizer has certain regularity, and I know the set where this is greater than 0. So if you compute this and you know that a priori u is a minimizer, then the derivative of this function at 0 has to be 0, and this holds for any phi. And when you do that, you realize that u has to satisfy an equation of the form Laplacian of u equals to gamma u plus to the gamma minus 1. Okay, in the set where u is greater than 0, and in the set where u is on the boundary then basically you have that the gradient of u is 0. Okay. So these are the conditions that basically appears when you take this derivative. Now the question is, how do we know that this develops a free boundary? What do I mean with this? So basically, notice that in here we're taking the positive part. When you have a functional of this sort, it is always cheaper to take function that doesn't change sign. So if you have a function that changes its sign, you just take the absolute value in here and you decrease the energy, because the L2 norm of the absolute value of u is always lower or equal than the Dirichlet energy of the original function. So it's cheaper always to selecting here something that it has one sign, basically, that is non-negative. So what we are saying here is that the non-negative functions can have minimums on the set. And why is this happening? Basically, this is happening because the power that we have in here, this gamma, as I said before, is between 0 and 2. So this power in here is between 0 and 1. So the right-hand side is just a Helder function. On the nonlinear part is just a Helder function of u. So this implies that in general, the solution in here doesn't satisfy this operator in here doesn't satisfy the maximum principle. So let me stress on this because this is quite important in semi-linear PDE. So let me make this remark. When we have equations of this form, in a set omega, and we know beforehand that u is greater or equal than 0 everywhere in omega, and f is a function that is Lipschitz, and such that f of 0 is 0, then we can apply the maximum principle to show that actually u is strictly greater than 0 if it is. Either u is strictly greater than 0 or u is identical to 0. And this is just because f is Lipschitz and satisfies this condition in here. Why? Because you can rewrite the equation as Laplace of u equals f of u times q. And then this in here is a bounded function because it's just the quotient of f of u over u, and it's Lipschitz, and this is satisfied. And when you have a solution of something like this, then you know beforehand that u is greater or equal than 0, then this cannot have zero minimums, basically. So a key point in here to develop free boundaries is this, to have this power. When gamma is equal to 2, then we don't have any free boundary to be studied. So there are another two things that I...
Daniel, you need that f is positive, no? The derivative is positive on 0.
No, we don't need it because of this. Basically, you can apply the maximum principle when you have one sign on the. You can apply Hobbes' lemma when you know. Okay, so this is important. You know that the maximum principle is satisfied in general when C has a sign, but in here we don't need the sign when you know that U is vanishing at the point. So I'm going to make the remark. So Hobbes' lemma. That is basically the lemma that says that when you have an equation of this form, on a domain, and you know that u is greater or equal than 0, then basically the normal derivative at the boundary has a sign. I mean, when you hit the boundary, you go with a negative slope. This requires C to have a sign, basically, but when you know that u is exactly 0, u at this boundary point is 0, then you can prove it regardless the sign of C. But yes, this is important. But in general, we only need f to be Lipschitz. Okay. So what I was going to say is that basically, when we are taking minimizers in here, there are two regimes basically. When gamma is between 0 and 1, and when gamma is between 1 and 2. When gamma is between 1 and 2, this is a convex power. So this implies that this problem is convex. So we have unique minimizers. And when we have unique minimizers, and when the problem is convex more in general, then these two things are equivalent. Any critical point is a deminimizer, and vice versa. Now, if gamma is between 0 and 1, this is a non-convex problem, and we may have different minimizers, and there are different ways to obtain solutions. So this is not enough to conclude full regularity and to conclude all the properties that you can expect from a minimizer. So you can cook up in here different kinds of solutions. You can use Perron method to obtain largest subsolution, the minimal super solution, and the minimum energy from here. All these three solutions don't agree in general. Okay, now this being said, I'm going to tell you basically what do you do when you're facing these kind of problems, these free boundary problems, and which are the two archetypical free boundary problems that you can obtain taking particular values of gamma. The first one is the obstacle problem when gamma is 1, and the other one is the Bernoulli one-phase problem when gamma is 0. So I'm going to talk a little bit about these two, and then tell you the general strategy to understand the regularity. Any questions so far?
This equation, Laplacian of u equals c of x times u, is it a kind of eigenvalue problem?
Yes. Okay. Actually, yes. And that's why Irene was asking for the sign, because you know that in general, if this is negative, if c is negative in here, you can have something like this, that is the eigenvalue problem, and you don't expect maximum principles in here. Actually, you have maximum principles for this operator whenever this is positive, and then you can apply all the theory that you know already for the Laplacian.
But c of x is a function.
But in here is a function, yes. Yeah, but if this is a function that has one sign, in this case, if it has a positive sign, if f is positive, then this, if you see all of this as an operator, now this is the whole operator, not the right-hand side and the operator, this operator satisfies the maximum principle. Yeah, that was the main point. Okay. So I'm going to give you two examples now. The first example is the obstacle problem. So basically the obstacle problem corresponds to the case when gamma equals 1, but it can be seen in a more geometric way as follows. Basically the obstacle problem consists in minimizing the Dirichlet energy over the domain with the restriction of u being greater or equal than some obstacle psi, that psi is a function that is already defined on the domain, and you ask also u at the boundary, basically, to be greater or equal than the obstacle on the boundary as well. And this is happening on the domain. Okay, so what is happening here geometrically? What is happening is that basically you want to minimize the Dirichlet energy. So what you want to be I don't know, a harmonic function, or you have an obstacle below. Let's say basically that this is your obstacle psi. We're working in R, and you have a prescribed boundary in here. Let's say -1 and 1. And when you minimize the Dirichlet energy, what you obtain is a function that has to be linear because it's harmonic, that detaches from the parabola in here. And basically you obtain this by taking all harmonic functions that are above the obstacle and you start lowering them until you hit the obstacle. So this is a sort of membrane, and you are lowering the membrane until you hit the obstacle, and then you continue bending the membrane until you hit the boundary values. And basically that's the solution. So the geometric procedure I'm describing is the Perron method. You take a super solution and you start lowering it until you hit the boundary, until you hit the obstacle and then the boundary. But either doing this or going through the energy is equivalent, because this again is a convex problem. This is a convex functional over a convex set, so you have a unique solution. Okay. Now, this is the free boundary basically when you detach from the obstacle. When you just detach from the obstacle, basically you obtain the free boundary. Now, if you subtract the obstacle in here, if you consider u minus the obstacle, and you rephrase all the functional and you normalize, then you end up having something along these lines. That instead of minimizing having an arbitrary obstacle, your obstacle will be 0. In here, notice that you are asking u to be positive. You are taking the positive part. So this is basically saying the following. So let me continue here. So this is basically saying the following. When you make a sort of change of variables, subtracting the obstacle, then you ask now u minus the obstacle to be greater or equal than 0. You normalize such that you get a 1 in here, in order to get an f. And when you minimize this function, what you're obtaining is something that satisfies this PD. Basically, Laplacian of u is 1 when u is positive and 0 otherwise. And therefore, if you do a picture of this, Laplace of u equals 1 is almost a paraboloid, and then you have to truncate it at 0 because you have the obstacle in here. So it's a paraboloid truncated, and this is the free boundary. Okay. Now, the other case that is very celebrated in general is the case when gamma equals 0. When gamma equals 0, it's basically a limit. So the other case is also called the Bernoulli one-phase problem. That is recovered when gamma approaches to 0 from the right. And basically the energy functional in here is the Dirichlet energy plus, and when we take the limit in here, when gamma goes to 0, basically this becomes the characteristic set when u is greater than 0. So if u is greater than 0, then this is 1, and always is array 0. So this is the characteristic where u is greater than 0. So we have in here two integrals competing: the Dirichlet energy and the set when, and the measure of the set where u is greater than 0. So if we look at this from the point of in the one-dimensional setting, and we prescribe, let's say, a boundary value, let's say use 1 in here, we'll notice that the solution basically will be a line that takes some value in here. And again, what it's computing is the measure of the set. So the larger the non-zero set, the positive set, so this will be larger. And the steeper the function, this will be larger. So basically we have a balance between how steep we're going down and how much positivity set we're allowing, basically. And if you, again, try to minimize this via the procedure that I did before, like adding a function, you obtain the PDE that is satisfied by the solution of this equation, that is the Euler-Lagrange, the so-called Euler-Lagrange equation, that says that the Laplacian of u is 0 in the set where u is greater than 0, and the gradient of u is prescribed at the boundary and is equal to 1. So this is completely determined what is the linear solution of this, that Laplacian of u equals 0 means that it is linear indeed, and gradient of u equals 1 indicates what is the slope. And if you change in here this by lambda, then you deduce in here that this has to be the square root of lambda, and this determines completely the slope. Because notice that this makes this basically gives a weight to how much you have to pay for the 0 set. Okay, now in here, if you go to the picture in Rn, what you will deduce is basically that solutions for this are almost planes that may wiggle a little bit, and when they enter to the 0 set, they have the gradient prescribed. So in the obstacle problem, morally the solutions detach from the free boundary in a quadratic fashion. So and in here, morally the solutions detach from the free boundary in a linear way. So this is the main takeaway from these two examples.
gamma is between 0 and 1,
Mhm.
you get like interpolation between that linear thing and that parabola.
Yes, exactly. I'm going to tell you a little bit about that right now, to tell you what is the profile of a solution for general gamma. And basically, understanding how the function detaches from the pre-boundary is the key point to understand what is the optimal regularity of both the function and the pre-boundary in the end. So, as you have seen so far, I have shed some light in these toy examples that are by themselves quite important problems in the field of elliptic equations by means of the one-dimensional case. So let's do the same in the one-dimensional case for the general equation that we're working in, that is this one. By the way, I haven't told you the name. This equation doesn't have a name by itself because it doesn't come from a celebrated mathematician, but it was studied by a student of Caparelli and an important German mathematician, and that's why it is called in the literature as the Alt-Phillips free boundary problem. So in the sequel, I will refer to it like this. So this is the equation, and therefore, if we go into the one-dimensional setting, so in 1D, I have y double prime equals to y to the gamma minus 1, and we expect the solution to be a power, like in the case of the Bernoulli one phase that is linear in the obstacle problem that was quadratic. So if we make a guess in here of y being of the form x to the beta, and we plug it in here, we realize, I will save you the algebra because I have written down this power so many times. If you put in here the second derivative of this, plug this one in here again, and then you solve for beta, you realize that beta has to be of the form 2 over 2 minus gamma. And this is basically the interpolation that Eduardo was asking about. If gamma is 0, we obtain 1, linear growth. If gamma is 1, we obtain 2, quadratic growth. And as gamma approaches to 2, this goes to infinity, implying that basically we are not having any free boundary when gamma approaches to 2. And this is natural because I told you when gamma is 2, we don't have any free boundary because the right-hand side becomes a Lipschitz function. Okay. Now, and in general, what happens with solutions of this equation is the following. So I'm going to tell you a little bit about the regularity. I'm going to make a table to make it easier. So I'm going to talk about regularity of solutions of the PDE of U, not about regularity of the pre-boundary so far, just of the function by itself. So first of all, when we have a PDE of the form Laplacian of U equals F, there is almost free regularity applying classical theorems. For instance, there is this classical theorem of Calderon-Sigmund that says that if this is in LP, then U is in W2P. Basically, U has two weak derivatives that are in LP. From there, if U is in W2P, then we can use Sobolev embeddings and improve the regularity and do a bootstrap argument, etc. But all in all, because of the free boundary, this process stops. And I will tell you how it stops. So I'm going to make a table in here where we have values of gamma, and we have in here the regularity. Okay, so if gamma is 0, this is the Bernoulli case. Basically, the best that we can get is U being Lipschitz, because you know it enters in here. You only know that the gradient in general is bounded. So the regularity for U is Lipschitz. When gamma is 1, and this is the obstacle problem, the best that you can get is C11. This is the second derivatives are bounded. And why is this? If you remember, the example that I depicted in here, even the one-dimensional example, tells you that the solution is something that goes linear up to here, goes linear up to here. So the second derivative of this is 0 because it's a line, of this is 0 because it's a line, but the second derivative of this is negative. So there is a jump in the second derivative. So this is sharp in general. And now, if you have a general gamma,
You get perhaps this 2 over 2 minus gamma regularity.
yes, except when it is an integer. When it is an integer, you don't pass through it. So if this is not an integer, then basically you have the integer part of here, the floor of this, comma the fractional part of this in here. And when it is an integer, then you get this minus 1, comma 1. Yeah, so this is it. This is the full characterization of the regularity for solutions. And the way to obtain it is basically, okay, you start with Calderon-Sigmund, and then to obtain the critical cases, like with Calderon-Sigmund implies the following. For instance, for the case of the obstacle problem, I will explain it briefly. It is not difficult to show that in the obstacle problem, the PDE that you're solving is this. So in here it is immediate that the right-hand side is bounded. This is in L infinity. Since this is in L infinity, then it is in LP for every P, and therefore U is in W2P for any P, and this is contained embedded in C1 alpha for any alpha. This is Calderon-Sigmund, and this is the so-called Morris embedding. Then you almost get the optimal regularity. For pushing this alpha into 1, you have to work a little bit more, but basically this is the sharp regularity. So this gives you an idea that the regularity by itself is not quite hard to prove in this. It's rather classical, and and basically it is dictated by the growth nearby the boundary. That's it. That's all that I want to say about the regularity. Now, I want to go now into the regularity for the pre-boundary and tell you how do you study boundaries and their properties. Because as in the basically setting up of the problem, in the setup of the problem, when I was telling you that there are two regimes depending on the value of gamma, also the pre-boundary behaves quite differently when gamma is between 0 and 1 or when gamma is greater or equal than 1. So, but there is a general strategy for studying pre-boundary regularity, that is inherited. This is inherited by the theory of minimal surfaces. And all this strategy was developed by Caffarelli and collaborators in a series of papers in the 80s and 90s. It goes as follows. The first part to study a pre-boundary problem consists in studying the optimal regularity of solutions. That we already discussed it in here in this table. Optimal regularity. Now, the second step is something called non-degeneracy. So basically, I told you the following. Out of this regularity, we have, for instance, that when you are working in the obstacle problem, when you detach from the pre-boundary, since the solution is C11, you can make a Taylor expansion. And notice that U of x, when, let's say that this is 0, is a point on the pre-boundary, U of x is equal to U at 0, that is 0, plus gradient of U at 0 dot x, but this point is a minimum point because U is greater or equal than 0 and is hitting 0 in here, so this is 0 again, plus an error that is quadratic because U is C11. So basically from here we deduce that U grows at most as a parabola. So out of the optimal regularity we have that U divided by the distance to the pre-boundary to the right power is bounded. So this is telling you that you cannot grow more than the distance to the pre-boundary to the right power. For instance, in here, we obtain quadratic growth, but in general, this is the bound that you can get. U is less or equal than a constant times the distance of x to the free boundary. Okay. Now, the question is, can a solution of one of these free boundary problems be super flat, like go less than quadratic and try to go, I don't know, like to the 100 power, to the 200 power. So that is what is called non-degeneracy. The solution is degenerate if it goes very flat outside. It is detaching quite flat from the pre-boundary. And then the second property that you always want to prove for a pre-boundary problem is a non-degeneracy problem. So the non-degeneracy problem basically says that when you consider U over the distance of x to the free boundary, I wrote in here omega, but omega is basically U greater than 0. When you consider U over the distance to the right power, this is not only bounded from above, but it's also bounded from below. So you know that all solutions have to grow more or less according to the right power that you already identified. So this is the so-called non-degeneracy property. So once you have these two properties about the free boundary, now what you are going to do is to do something that is quite common in elliptic problem, and is to zoom in nearby the free boundary. This is a so-called blow up. So what you do is to see what is the behavior of U exactly at a point of the free boundary in the following way. So this is the third step, that is considering blow-ups. So what is a blow-up? Basically, you have in here the solution of your problem, and you want to know nearby this point, 0, how this is growing outside. So what you do is to consider U of R of x, where R is something between 0 and 1. So you're zooming in nearby the point, nearby 0, and then you're rescaling in a quadratic way to see what is happening at a quadratic level in here. And why is this convenient? Because if you consider this function, UR of x, and you apply the Laplacian, then you obtain R squared times, you obtain R squared because of the Laplacian in here, the characteristic of U greater than 0 over this R squared. So the equation is also satisfied by these rescalings. So the main advantage of doing this at first is that the equation is homogeneous with respect to this scaling. So what you're obtaining here are solutions of the same equation in a different level, and therefore because of this property in here, and because of the regularity that you already have, then this sequence is pre-compact thanks to the Arcelor-Ascoli theorem, and therefore you can take a subsequence that converges uniformly. So this will converge uniformly as R goes to 0 to a global solution in the whole Rn, U0, U0. And now, depending on how is the solution, you can guarantee that either this point in here behaves regularly in the sense that you don't have like a cusp or something like that, and therefore you are differentiable nearby the free boundary. So for the case of the obstacle problem, I can tell you precisely where are the possible profiles that you can get when you take limit when R goes to 0, and are basically the following two. So what we're finding is that when R goes to 0, then you have a solution of this problem in the whole Rn, And there are two types of solution. The first type of solution that you expect, if this is, let's say, this is our free boundary. This is our free boundary, let's say. Imagine we have the parabola that is coming out. There are some points in which the parabola is just taking, the parabola is just hitting the zero in a line, like this. It's hitting like this. But there are other points in which you're basically truncated it. And therefore, if you zoom in one of these points, you expect it to rectify, and in the end, see the function being positive in here and being zero over here. So when you make the zoom in, at these points, there are ostensibly regular points because the boundary is regular at those. Then what you obtain is that ux will be equal to x dot e squared plus, where e is basically the normal vector at the free boundary. So this is a regular blow up. When the free boundary is regular, you expect to have one of those. And actually, this is a theorem, a celebrated theorem of Caffarelli in a paper in Acta of Mathematics that says that whenever the blow up at a point has this structure, then the free boundary is C1 alpha nearby that point. Now, if you are in contrast in one of these, basically what is happening is that nearby, the function is positive, and therefore the zero set of your blow up will be one dimension less or two dimensions less, depending on how many, what is the density of the non-zero set around the point. Then we have the singular blow ups. Then we have the singular blow-ups. Where u naught of x equals a quadratic functional of this sort, where the trace of a is 1 and a is positive semi-definite. So basically, instead of having a function that is truncated after one point, the graph of this is basically a paraboloid. It's a paraboloid that is truncated, and here is 0, and then it detaches. What we get in here is basically one paraboloid where the zero set is either 0-dimensional or 1-dimensional. And this corresponds to singular points in the free boundary, in this sense, that basically you don't have a manifold, but what you have, or at least you have a manifold of one dimension less. That's basically what is happening. Now, then, according to the list that I was doing, once you have the blow-ups and you classify them, basically you get either regular points or singular points. In the regular points, then by a standard theory, you can show that the free boundary nearby those points is C1 alpha. In the singular points, you're doomed. Basically, they are singular. You can not expect more than that. So, what I want to say in the last how much time do I have? 10 minutes?
25 and 20.
20, okay. Yeah. What I want to say in the last 20 minutes is basically, how do you push further the regularity from C1 alpha to C2, C3, C infinity? And I want to make the example with the obstacle problem because as so far I have explained pretty well the theory for this particular instance. In general, in the other cases of gamma, everything is more or less open for the higher order regularity. I'm currently developing the theory with Xavi Ros-Oton from the University of Barcelona. Then, but the philosophy is more or less the same. So I'm going to explain it with with the obstacle problem where the solutions are pretty straightforward and we don't have any u to the gamma in here that is going to mess around because of the nonlinear behavior. So let me explain in the rest of the talk how do you go from C1 alpha to C infinity. What is the philosophy behind it? That would be the fourth step. So the fourth step, how to go from C1 alpha to C infinity. Okay, so the tooling here, or the tools that I'm going to use, a sort of Liouville theorem. In the spirit of complex variable, basically a solution, so classification of solutions, of global solutions for PDEs with growth. So we know that the most simple case for a Liouville theorem is that if you have a harmonic function in Rn such that the infinity norm in a ball is of this form, then U has to be a polynomial of degree at most m. So in this spirit, I'm going to use a Liouville theorem to classify global solutions, and the other thing is a compactness argument. Okay, so I'm going to tell you now what will be the general strategy using these two ingredients to go from C1 alpha to C infinity. It's pretty straightforward, and I think it's quite enlightening because it can be applied to problems that are not even from free boundary, but are from, I don't know, differential geometry when you parameterize nearby the solution by graphs. And the idea is pretty simple. So we want to study the regularity of a level set of a function. So we want to study the regularity. We want to understand the regularity of the set U equals O. That is, more speaking, the set U equals 0. And therefore, what we are going to do is to see what is the normal of U in here. Basically, the normal of the free boundary is, morally speaking, gradient of U normalized. I'm saying morally speaking because, for instance, in the case of the obstacle problem, in here the gradient is 0. So this is not well defined a priori, but you can approximate it by other level sets. Let's say U equal epsilon and epsilon going to 0, and do the following trick. And this trick is the main concept that allows you to understand how to use these two techniques to improve the regularity. The trick is the following. So we can write this down as U1, U2, UN. They are the partial derivatives, and the norm of the gradient is basically the sum of U j squared. Now, if you know that the normal at some point, let's say at this point, goes in the nth direction, then what you want to do is to divide everything in here by the derivative in the nth direction, and you proceed as follows. Dividing everything by UN. Okay, so what is going to happen in here? when you divide everything by UN, then the denominator will have just the sum from j equals 1 to n minus 1 of the quotients plus 1. So this will never vanish. So if you show that this is regular, the quotient of uj over un is regular, and the quotient of ui over un from I equals 1 to n minus 1 are regular, then you have a quotient of two functions that are regular, and the denominator is never vanishing. So if ui over un is ck, then the normal vector in here will be ck. And if you show that the normal vector is ck, then the surface in here will be ck plus 1. So this is basically indicating that if we want to understand what is the regularity of the free boundary, it suffices to understand what is the regularity of quotients of partial derivatives of the function.
It doesn't matter if you take you divide by another variable.
You have to select one that you know that is not going to vanish in some sense. I mean,
Okay.
what I'm saying is that we know that u behaves like, in the case of the obstacle problem, like the distance square. Now, if you take certain partial derivatives, if you take a partial derivative, this is true, is less than linear, because if you take derivative in the distance square, you get the distance, morally. But there is one that will satisfy this. All of them will vanish, except for the one in which the normal will be pointing out. So there is one direction in which the normal will grow, will be non-degenerate with respect to the distance. So you have to select wisely which of them you're going to divide, because in some cases, this will go to 0. So yeah, there is one for which this works.
And this one doesn't change, it's always the same. You can.
No, you have to rotate. I mean, when you make this procedure, you can always do it up to rotations or shifting, because the equation is invariant with respect to shift or rotation. Yeah, you always have to, you can assume without loss of generality that the nth derivative is the one that works for this purpose. Okay. Now, so out of this discussion, we see that the normal will be C alpha or CK whenever the quotient of two partial derivatives is CK. And therefore, this is what we're going to do. We're going to prove that quotients of partial derivatives have regularity. Okay, I think I'm going to do it in here as well. Okay, so here's the thing. When we have the solution satisfies this. So if we take a partial derivative of this equation, there will be harmonic in the set where u is greater than 0. So we are just trying to understand the boundary behavior of harmonic functions in the set where u is greater than 0, and we know that this set, the boundary of this set, nearby the point we are studying, is already C1 alpha. So it's already regular because we are studying it at regular points. So now what we want to do is to show that actually ui minus un, that is the other partial derivative, this function in here, times a constant, decays like the distance to the boundary, the 1 plus alpha. So what do I mean with this? Basically, what we want to show is that this function in here is C alpha, is C1 alpha. Because we want to show now that the boundary is C2 alpha. We know beforehand that the boundary is C1 alpha. So if we show that the quotients of partial derivatives is C1 alpha, then we gain 1 degree of regularity. We will get C2 alpha. So now the question is, how can we prove that a quotient of two functions is C1 alpha? Then the general strategy is to show first that the difference is dominated by some power of the distance. And if you show this, then by some basic algebra, you can show that actually this is the case. Okay. So in order to prove that there exists a constant that we don't know yet, such that this behavior is satisfied nearby the boundary, then this is where the strategy comes. Basically, what we do is to proceed by contradiction, contracting this inequality in here. I'm going to tell you this real quick and then conclude. So what you do is the following. So we go by contradiction. This argument is pretty elegant and simple. You go by contradiction, and you assume that for any sequence of constants, you can find a sequence of functions. Sorry, for any. Sorry. So what you're going to do is the following. We're in here. This is the point that is regular. You want to show that the result holds in a ball of radius r surrounding the point. So you proceed by contradiction, assuming that there is a sequence of radii going to 0, such that in this ball, the L-infinity norm for any sequence of constants ck, the L-infinity norm of this is greater or equal than r to the 1 plus r. Yeah, so you proceed by contradiction, assuming this, and then
Can you repeat the first part?
Yes.
You select the RK or the CK?
Yeah, so sorry. So I was saying that what you want to show is that an inequality of this type holds for a ball surrounding the point in which you're regular for some radius, and then you proceed by contradiction and you say, okay, let's suppose that this doesn't hold, so it means that there is a sequence of radii surrounding the point that are shrinking to 0, such that in no one of these balls the estimate holds, so it implies that the L-infinity norm of this divided by the distance, that in this case becomes just the power of the radius, blows up, basically. And this is the infinity norm in the corresponding ball. So you show this. Then by contradiction you have this. And then you define a sequence of functions, a rescaled sequence of functions, that is basically ui rx minus un rx over this. And you basically showed that this guy, when r goes to 0, converges to a function that satisfies the equation that satisfies this. So the strategy is to go by contradiction. Suppose that you can go by contradiction, then define a rescaled version of your function, show that it converges to a harmonic function in the whole space, actually in Rn plus, and show that also this function here has a growth of this sort, and therefore because of this because of Liouville's theorem, you can show in the end that this has to be basically a linear function. There is no other option. If you have a harmonic function in the half space that grows like this, then it has to be a linear function. And I was saying at the beginning that we don't know beforehand what this constant is. Therefore, when you do the contradiction sequence, you have to pick up these CKs, and you pick these CKs such that ui minus ck un is orthogonal to un in L2. So basically, this ck is the best linear approximation in the terms of mean square error. So this is basically a projection in Hilbert space, such that this is 0. And in the end, when you take the limit, since un is the derivative of the solution of the obstacle problem, this converges to a linear function because converges to the distance. So in the end, you show that this is orthogonal to all linear functions, and therefore by Liouville, this has to be a linear function. But at the same time, it's orthogonal when you take the limit. This will be orthogonal to linear functions. Then this guy in here has to be 0. So this is the strategy in general. You go by contradiction, show that you have convergence, you pick up the constants such that the sequence of, that you are picking up in here is orthogonal to all the set of solutions, therefore it has to be trivial. But the problem is that it cannot be trivial because you normalize it to have L infinity norm equal to 1 in the process. And in the end, so the compactness argument is to guarantee the existence of a global solution. The Liouville theorem is to determine what is the class of all possible solutions. And in the middle of the process, you select constants such that you can kill all the kernel of your operator or all the solutions of the Liouville theorem. And basically you obtain a contradiction and you deduce that this has to happen, but this constant is not known because you obtain it by compactness and linear approximation. So this is the strategy, more or less, that is pretty general and that works for many kind of obstacle problems that I wanted to tell you about, basically. Yeah.
Okay, so thank you very much for your talk, Daniel. Any question, comments? No? Okay, so...
I want to know if we have another kind of blow-up for the other problems, not only for the obstacle problem.
Okay, so the thing is that in the case of the obstacle problem, we have these regular blow-ups and the singular blow-ups. The problem is that only for the obstacle problem, all the blow-ups have been classified. For all the other values of gamma, we have it, for instance, for the Bernoulli one-phase problem, remember that the solutions are harmonic functions. So you can show that blow-ups for the Bernoulli one-phase problem are harmonic functions in cones. So those are harmonic functions in cones, and they are pretty well studied. And yeah, this is the classification, but we don't know how are all the possible blow-ups, because the harmonic functions in cones may have the property that, I don't know, you have several connected components of the cones, and therefore you can have a solution for each. So for instance, you have one in here, another one in here, another one in here. This cannot happen in R2, but in R3 can happen, or in R4. Now, for the case of the general Alt-Phillips problem, the regular blow-up has this form, as in the obstacle problem, but we don't know yet what are the singular blow-ups when n is greater or equal than 3. For n equals 2, there is a recent paper of 1 week ago of Baldinocci where he classified all of them, but there is nothing more known